welcome back everybody. This video is the follow-up video to the one before where we talked about state estimation in general. Now we talk about a specific state estimator, which is the linear Kalman filter, as a very simple example for a Kalman filter. In the next couple of videos, we will be talking about different types of Kalman filter, but for now, let's stay with the linear one. So before, when we talked about the state estimator in general, we made some assumptions, which we will continue now, that we will be looking at linear systems and that our noise stays the same. So why use a Kalman filter? A Kalman filter in general can be considered an optimal estimator where we find the best estimation, best in quotations because there can be better, but this is, for a simple example, the best estimation we can get. And also the Kalman filter, besides being best, is also recursive. That means we do not need to store our data. We can use it continuously as it arrives. So not in like batch processes where we usually have all the data in the beginning or needed in the beginning. For a linear system, we can use our online estimation. So it's very important if we want to use this during processes, like for example, which we talked in the last video, the biomass concentration, because those are values that a lot of times only get measured directly every 30 minutes, every hour, sometimes only 3 to 4 times a day. So with a Kalman filter, we could predict the state for the biomass online for like every minute, every 30 seconds, depending on whatever we're doing, but recursively all the time. So that makes it easier for us to control and predict how our process is going during that time. So, but how does our Kalman filter work? Our linear Kalman filter. So in the last video, we talked about 3 steps every estimator or during the composition of the estimator we take. We first predict. Second, we correct our previous estimation. And then update. Those 3 things change depending on the Kalman filter, but are always the same for every estimator. So for every state estimator. So specifically for our Kalman filter, where we're still in the linear system with Gaussian noise, we do have to consider some things. So in the last video, we talked about our different matrices we need. So for one, we have the V, which is our sensor noise, and the W, which is our process noise. Both are considered, but in addition to those matrices, we also need to consider our P, which is our covariance matrix. So for P, which we didn't talk about last time for the Kalman filter, we will calculate this one with P, with is the covariant matrix, E, which is our mean, and our current state, and our estimated state. So, like this. So how do we do the estimation with the Kalman filter? We still stay on the 3 steps, these 3 here, but those are a bit different than the ones we've already learned about last time for the simple state estimator. For the Kalman filter, we'll do the 3 steps, but the equations and how we do it will be a bit different. So we start off with our prediction. So now that we do consider our covariant matrix, we still have the state estimation, the current one, which stays the same. And the change later is only in the correction. So we stay the same as for the simple one. But we add the prediction or our covariance matrix, which is okay. So what do we have here for P? We do have our state transition, which we had last time. And we also have Q, which is our process error matrix. So a matrix for all the errors that we could find from the measurements from our process. So this is our new prediction, like in difference to the last time. We now then compute the correction again. This time, as this is a Kalman filter, not a simple state observer, we also will calculate something that is called a Kalman gain, which is specific to the Kalman filter, which we call L here. There are some other notations. We could also call it a big or a capitalized W. Sometimes G is used, but in our case, G is something else. So we will stay with L. And for the Kalman gain, you need the covariance matrix. And H, which is our observation or measurement matrix. And S. We call this S just for notational purposes only, as this makes it easier to write this all up. S, we do calculate, again, from H, our covariance matrix. And R. R here is our measurement error. So with this, we can then calculate the correction, so X, which is the difference between our first estimation and our corrected estimation. For that, we do use L, our Kalman gain, our measurement at state K. Again, H. And our state at K, K minus 1. Like this. So with this, like last time, we do have our correction, which we can then use to update our prediction in the next step. So again, we update. And to update, we do have two steps. We first update our state estimation and then also update our covariance matrix. So first, the update of our state estimation at state K and K. We have our previous estimation, K, K minus 1, plus the Kalman gain times delta y. Delta y is our measurement residual. We will not cover the calculation of this one in this video because it would be too long, but it will be in the script. So to find out how to calculate the update, look in the script. Okay, so after we updated our state estimation, we also need to update our covariance matrix, which is P. This time also at state K and K. We have our previous covariance minus the Kalman gain times S and times the Kalman gain transposed. So these three steps are the same ones as for the simple estimator and will be in the end also the same steps for the extended Kalman filter. If our system is linear and especially our noise is Gaussian, then the linear Kalman filter minimizes the mean standard error, the MSE, over all filters and is therefore a good estimator or a good application for most linear systems. But why is the linear Kalman filter not something that is optimal for everything? So, because again, like in the last video, our assumptions are that the system is linear and our noise is Gaussian as always. But what if we do not have a linear system or we do not have Gaussian noise? Then the linear Kalman filter does not give us the, in quotation, best estimation. For that, we need something else. So when we do not have a system like that, we have two options. We can either do something that is called an extended Kalman filter and an unscanted Kalman filter, short EKF or UKF. Those two, for other systems than linear, we will talk about in the next video.